All right, let's go. Number 10. Jupiter's atmosphere revealed in unprecedented detail. Storms, auroras, and hazes that no previous telescope could see. When the James Webb Space Telescope turned its golden mirror toward Jupiter in the summer of 2022, scientists expected sharp images. They were not expecting to be genuinely stunned. The images that came back, processed by citizen scientist Judy Schmidt from raw data released by the Webb team, showed Jupiter in near-infrared wavelengths with a clarity and a richness of detail that left planetary scientists scrambling to explain features they had never previously been able to observe simultaneously in a single image. The most immediately striking feature was the auroras. At both of Jupiter's poles, Webb captured auroral emission in extraordinary detail. Glowing rings of infrared light produces charged particles from the solar wind and from the volcanic eruptions of Io spiral down Jupiter's magnetic field lines and collide with the upper atmosphere. These auroras are far more complex in their fine structure than any previous observation had resolved, showing filamentary, rapidly varying patterns that indicate turbulent magnetospheric dynamics operating on timescales of minutes. Simultaneously, Webb revealed a network of hazes at high altitudes above the main cloud deck, diffuse, wispy structures that previous telescopes had detected only as broad, smooth features, but that Webb resolved into discrete, structured layers with distinct boundaries and compositions. The Great Red Spot appeared not as a uniform oval, but as a complex, thermally structured vortex with internal temperature variations and compositional gradients visible for the first time. Thin rings of dust surrounding Jupiter, previously known to exist but never imaged in detail from a space-based infrared observatory, appeared clearly in the wide-field images. The combination of auroras, hazes, cloud structure, ring detail, and multiple moons all captured simultaneously in a single observing session demonstrated that Webb's capabilities for solar system science, which many astronomers had considered a secondary mission goal, were exceeding expectations as dramatically as its deep field imaging. Jupiter has been studied for 4 centuries. Webb made it new again in a single night. Number 9. The most distant individual star ever detected, a single stellar flare from 12.9 billion light-years away. Before the James Webb Space Telescope, the most distant individual star ever detected was a blue supergiant nicknamed Earendel, identified in 2022 in Hubble Space Telescope data at a redshift of 6.2, corresponding to a distance of approximately 12.9 billion light-years, when the universe was just 900 million years old. Earendel was detected through extreme gravitational lensing by the galaxy cluster WHL 0137-08, which amplified the star's light by a factor of thousands, making the detection of a single star at cosmic distances possible for the first time. The discovery was considered extraordinary, a single star visible across more than 90% of the observable universe's history. Then, Webb pointed at the same galaxy cluster with its infrared sensitivity and confirmed Earendel's detection with a precision and detail that Hubble could not approach. Webb not only confirmed the star, but resolved its color, its spectral energy distribution across near-infrared wavelengths with sufficient precision to constrain its temperature to approximately 13,000 Kelvin, identifying it as a hot, massive blue supergiant with a luminosity potentially exceeding 1 million times the sun's output. Webb's data also suggested that Earendel may not be a single star, but a tight binary system. 2 massive stars separated by distances too small for any telescope to resolve directly, but whose combined spectral signature is inconsistent with a single spectral spectrum. More remarkably, Webb detected additional gravitationally lensed individual stars in the same arc as Earendel, a population of ancient massive stars from an epoch when the universe was less than 1 billion years old, individually resolved through the extreme magnification of the galaxy cluster lens. Each of these stars is a sample of the first stellar populations, formed before the universe had been significantly enriched by heavy elements from supernova explosions, potentially including some of the earliest massive stars in the observable universe's history. Webb converted a single extraordinary detection into a population study of the most ancient individual stars ever observed. Number 8.
carbon dioxide definitively detected in an exoplanet atmosphere, a milestone that changes the search for biosignatures forever. Before the James Webb Space Telescope began science operations, the detection of specific molecules in exoplanet atmospheres was possible in principle, but brutally difficult in practice. The Hubble Space Telescope had detected water vapor, sodium and potassium in hot Jupiter atmospheres, and had reported tentative evidence of carbon dioxide in a handful of systems. But the word tentative was doing significant work in all of those detections. The signal-to-noise ratios were marginal, the identifications ambiguous, and the scientific community appropriately cautious about claims of specific molecular detections in any exoplanet atmosphere. In August 2022, the Webb team published the first unambiguous high-confidence detection of carbon dioxide in an exoplanet atmosphere. The target was WASP-39b, a hot Saturn-mass planet approximately 700 light-years from Earth, and the detection came from Webb's NARSBE instrument observing the transmission spectrum of the planet as it transited its host star. The carbon dioxide absorption feature appeared in the spectrum with a signal-to-noise ratio so high that it was immediately recognizable and unambiguous. This was not a marginal detection requiring careful statistical argument. It was a clean, obvious spectral feature of the type that textbooks use to illustrate molecular identification, appearing in an exoplanet atmosphere for the first time in the history of astronomy. The significance extends far beyond WASP-39b itself. Carbon dioxide is one of the primary biosignature-adjacent molecules that astrobiologists have identified as both a potential indicator of planetary habitability and a marker whose combination with other molecules, particularly oxygen, ozone, and methane, could indicate biological activity. Detecting it unambiguously in a hot Jupiter establishes the observational baseline for the techniques and sensitivity levels required to detect it in smaller, cooler, potentially habitable planets. The WASP-39b detection was a proof of concept for the most ambitious scientific goal in the history of exoplanet science: the detection of biosignatures in a potentially habitable world's atmosphere, demonstrating that Webb's capabilities are sufficient to attempt it, not merely in theory, but in practice. Number 7. Stellar nurseries revealed in the Carina Nebula. Thousands of previously hidden protostars emerging from the cosmic cliffs. One of the first images released by the James Webb Space Telescope on July 12, 2022, the day NASA unveiled Webb's first full-color science images to the world, showed a region of the Carina Nebula called the Cosmic Cliffs, a dramatic, towering landscape of gas and dust approximately 7,600 light-years from Earth, where the intense radiation and stellar winds of massive young stars are carving away the edge of a giant molecular cloud, exposing the star-forming region within. The image was immediately recognized as one of the most visually spectacular astronomical photographs ever taken. But the scientific content of the image went far beyond aesthetics. In the infrared wavelengths at which Webb observes, the dense gas and dust that makes stellar nurseries opaque to optical telescopes becomes transparent, allowing Webb to peer directly into the regions where new stars are actively forming. Embedded within the cosmic cliffs image, invisible in any previous optical or near-infrared observation of this region, were hundreds of previously unknown protostars, young stellar objects still in the process of accumulating mass from their surrounding envelopes of gas and dust, glowing in infrared wavelengths as their gravitational contraction converts potential energy to heat. Many of these protostars were driving the jets and outflows discussed in a previous video's description of Herbig-Haro objects, their collimated plasma jets appearing as bright streaks cutting through the nebula's gas. The population of protostars revealed by Webb in a single image exceeded what had been cataloged in this region over decades of previous observations. The mass distribution, spatial distribution, and outflow properties of these newly revealed protostars are providing statistical constraints on the initial mass function, the distribution of stellar masses produced in a star-forming event, that previous incomplete samples could not supply. Webb did not merely image the Carina Nebula more sharply, it revealed an entirely hidden population of forming stars that previous telescopes could not see, transforming a well-studied region of the sky into a new scientific frontier in a single observation. Number 6.
the first direct detection of a quartz crystal cloud in an exoplanet's atmosphere, silicon dioxide particles floating in an alien sky. The atmosphere of the hot Jupiter WASP-17b had been studied extensively before Webb turned its instruments toward it. Previous Hubble observations had detected silicate features in its transmission spectrum, evidence that the atmosphere contains silicon-bearing particles of some kind, most likely in the form of aerosol clouds. But Hubble's spectral coverage and resolution were insufficient to distinguish between the various silicate mineral species that could potentially be present: ensitite, forsterite, quartz, or amorphous silica, each of which has a distinct spectral fingerprint accessible only at the mid-infrared wavelengths that Webb's MIRI instrument covers uniquely among space telescopes. In 2023, the Webb MIRI transmission spectrum of WASP-17b revealed a spectral feature at approximately 8.6 micrometers, a wavelength at which crystalline silicon dioxide, the mineral composition of quartz, produces a distinctive absorption signature that no other common silicate species matches. The identification was unambiguous. The clouds of WASP-17b are composed of quartz, crystalline silicon dioxide particles, the same mineral that forms beach sand, window glass, and the quartz crystals used in watches and electronics on Earth, suspended in the atmosphere of a gas giant 1,300 light-years from Earth at temperatures of approximately 1,500 degrees Celsius. The formation of crystalline quartz in WASP-17b's atmosphere requires specific temperature and pressure conditions that allow silicon dioxide to nucleate and grow into crystal structures rather than remaining in an amorphous glassy form. The detection provides direct information about the thermal and chemical structure of the planet's upper atmosphere at the specific altitude where the quartz clouds form, a level of atmospheric characterization that was simply beyond the reach of any previous observatory. Webb detected not just that clouds exist in an alien atmosphere, not just what mineral family they belong to, but their specific crystalline structure, a level of mineralogical precision applied to a planet 1,300 light-years away that exceeds what geologists could determine about many rock samples in the pre-spectrometer era of Earth science. Number 5. Gravitational lensing revealing galaxies from the first 400 million years, earlier than any previous telescope had seen. The Hubble Space Telescope's ultra-deep field, a long-exposure image of a tiny patch of sky representing 1/13 millionth of the total sky area, revealed approximately 10,000 galaxies at various distances and redshifts, with the most distant galaxies visible at redshifts of approximately 8 to 10. Corresponding to epochs approximately 600 to 700 million years after the Big Bang. This was Hubble's deepest view of the early universe, achieved through one of the longest single exposures in the telescope's history. It was considered the definitive observational boundary of the accessible early universe for the optical era of astronomy. Webb's first deep field image, released on July 11, 2022, the evening before the full first image release, covered a patch of sky approximately the size of a grain of sand held at arm's length and reached galaxy populations at redshifts exceeding 13, corresponding to epochs less than 400 million years after the Big Bang. The image contained thousands of galaxies across a range of cosmic epochs, the most distant being tiny, faint smudges whose redshifts were subsequently confirmed through spectroscopic follow-up as genuinely existing in the first few hundred million years of cosmic history. The gravitational lensing of the galaxy cluster SMACS 0723 in the foreground of Webb's first deep field amplified the light of background galaxies by factors of tens to hundreds, stretching them into arcs and dramatically multiplying the effective depth of the observation. Webb's combination of infrared sensitivity, necessary to detect the red-shifted ultraviolet and optical light of early galaxies, and its enormous mirror area allowed it to see farther and in more detail than any previous observatory, detecting individual galaxies from an epoch that Hubble could glimpse only as statistical excesses in photometric catalogs. The boundary of the directly observable early universe moved back by hundreds of millions of years on the day Webb released its first science images. Number 4. Methane and carbon dioxide together in the atmosphere of K2-18b, the strongest atmospheric biosignature candidate ever detected around the habitable zone planet.
K2-18b was briefly mentioned in a previous video in the series in the context of the tentative dimethyl sulfide detection, but the full significance of Webb's 2023 atmospheric characterization of K2-18b extends well beyond that single tentative molecule and deserves detailed examination as the most scientifically significant exoplanet atmospheric detection in the history of the field. Not because any single molecule detected is a confirmed biosignature, but because the combination of molecules detected in a habitable zone planet's atmosphere has never before been achieved by any telescope. Webb's NIR-CAM transmission spectroscopy of K2-18b confirmed the simultaneous presence of carbon dioxide and methane in the atmosphere of a planet orbiting within the habitable zone of its host star. This combination is significant because on Earth, the simultaneous presence of both carbon dioxide and methane in a planetary atmosphere requires a continuous source of methane production to counteract the rapid oxidation of methane by free oxygen and ultraviolet radiation. In Earth's atmosphere, that continuous methane source is overwhelmingly biological, the metabolic output of anaerobic microorganisms in wetlands, ocean sediments, and the digestive systems of animals. Abiotic methane sources exist, but are generally insufficient to maintain the atmospheric concentrations observed on Earth without biological augmentation. Whether K2-18b's methane is biologically produced or abiotic is genuinely unknown. The planet's hydrogen-rich atmosphere creates chemical conditions very different from Earth's, and abiotic methane production in a hydrogen-dominated environment may be more efficient than in an oxygen-dominated one. But the simultaneous detection of carbon dioxide and methane in the atmosphere of a sub-Neptune in the habitable zone represents the first time any telescope has detected the combination of atmospheric molecules that theorists had identified as the target of the biosignature search before Webb launched. The target was hit. Whether the arrow was fired by biology or by abiotic chemistry is the question that subsequent observations are attempting to answer. Number 3. The cosmic Webb filament directly imaged for the first time. Webb revealed the largest structure in the universe in visible detail. The cosmic web, the vast network of dark matter filaments connecting galaxy clusters across hundreds of millions of light years, has been mapped statistically through the distribution of galaxies in large surveys for decades. The theoretical models of cosmic structure formation predict that galaxies trace the underlying dark matter filaments clustering along these invisible highways of gravitational scaffolding, with vast empty voids occupying the spaces in between. The existence of the cosmic web as a structural feature of the universe is not in question, but directly imaging the gas that fills the filaments, the warm, hot intergalactic medium that traces the dark matter skeleton, has been extraordinarily difficult because this gas is diffuse, faint, and observable primarily in ultraviolet and soft X-ray wavelengths that are difficult to study from space. In 2024, a team using Webb's NIR-CAM instrument in an extraordinarily deep observing mode targeting a specific high redshift galaxy protocluster announced the first direct imaging of a cosmic Webb filament in emission. The target was a region of the early universe approximately 11 billion light-years away, where a dense concentration of galaxies forming in the first few billion years after the Big Bang was known from previous observations to be connected by filamentary structures predicted by simulations. Webb's image revealed a diffuse, extended emission structure connecting multiple galaxy groups across a physical scale of approximately 13 million light-years, a direct, spatially resolved view of the intergalactic gas tracing a cosmic Webb filament, glowing in Lima alpha emission from hydrogen atoms being ionized by the ultraviolet radiation of the surrounding galaxies. The image confirmed for the first time in direct observation the filamentary geometry of the cosmic web at the scale predicted by simulations, not as a statistical inference from galaxy positions, but as a directly imaged physical structure. The gas density, extent, and emission properties of the observed filament match simulation predictions with a fidelity that validates the cold dark matter framework of structure formation at the level of individual filament imaging rather than statistical ensemble properties. Webb saw the skeleton of the universe directly in a single pointing, revealing in hours what surveys of millions of galaxies had only previously implied statistically. Number 2. Protoplanetary disks in the Orion Nebula showing planets forming in real time and being destroyed simultaneously. The Orion Nebula is the nearest massive star-forming region to Earth, located approximately 1,350 light-years away, and it contains one of the most active and most observed stellar nurseries in the galaxy. Previous observations by Hubble revealed hundreds of protoplanetary disks, the flattened structures of gas and dust surrounding young stars from which planets form, as dark silhouettes against the bright nebular background. These proplyds, as they are called, were among Hubble's iconic solar system science contributions, demonstrating that planet-forming disks are common products of star formation. Webb's infrared observations of the Orion Nebula, published in 2024 as part of the PDRs for All program, a comprehensive survey of the photodissociation regions at the boundary between ionized and neutral gas, revealed the protoplanetary disk population in extraordinary new detail. Webb detected the thermal emission of dust in the disks directly, measuring their temperature profiles, radial structures, and compositions with a precision that Hubble's optical imaging could not approach. Individual disks showed annular gaps, rings of reduced dust density at specific radial distances from the central star, indicating the presence of forming planets sweeping their orbits clean of dust in precisely the way our own solar system's planets cleared their formation zones 4.5 billion years ago. Most dramatically, Webb directly observed the photoevaporation of protoplanetary disks by the intense ultraviolet radiation from the massive O-type stars of the trapezium cluster at the Orion Nebula's core. Disks located close to these massive stars were being ablated, their outer regions stripped away by the radiation pressure and ionizing flux, even as their inner regions continued to form planetary embryos. Webb measured the mass loss rates of these externally irradiated disks with sufficient precision to calculate their remaining lifetimes, finding that several disks close to the massive stars will lose all their planet-forming material within the next 100,000 years before the planet formation process can complete. Webb was simultaneously watching planets form and watching their formation be terminated in the same image, in the same star-forming region, demonstrating that whether a planet-forming disk survives long enough to produce planets depends critically on the specific stellar neighborhood where its parent star happens to form. Number 1. The confirmation that the early universe contains structures too large for any existing cosmological model, and the crisis is getting worse every year. This discovery was briefly introduced in a previous video in this series, the detection of early massive galaxies that should not exist according to standard cosmological models. But the full scope of what Webb has revealed since beginning science operations in 2022, the specific ways in which the observations are straining and in some cases breaking existing theoretical frameworks, and the scientific community's increasingly urgent response to the accumulating data deserves a dedicated and comprehensive examination. Because this is not a single anomalous detection. It is a systematic, growing crisis that is reshaping cosmology in real time. The standard model of cosmology, lambda CDM, combining a cosmological constant representing dark energy with cold dark matter, successfully explains an enormous range of observations, from the cosmic microwave power spectrum to the large-scale distribution of galaxies to the abundance of light elements produced in Big Bang nucleosynthesis. It has been the dominant theoretical framework in cosmology for approximately 25 years, and it has survived every observational test conducted during that period. It is, by any reasonable scientific metric, one of the most successful theoretical frameworks in the history of science. Webb has now identified multiple galaxy populations at redshifts between 8 and 16, corresponding to epochs between 200 and 600 million years after the Big Bang, whose number densities, stellar masses, and star formation rates exceed lambda CDM predictions by factors of 10 to over 100 in the most extreme cases. A galaxy containing 10 billion solar masses of stars, observed when the universe was just 500 million years old, requires a star formation efficiency, the fraction of available gas converted to stars, that exceeds theoretical maximum values derived from the physics of star formation by factors of 5 to 10 in the most optimistic assumptions. The gas supply available to form stars in dark matter halos at those early epochs, constrained by the growth rate of structure in lambda CDM, is simply insufficient to produce the observed stellar masses in the available time, even under the most optimistic assumptions about star formation physics. Each new cycle of JWST observations has added more candidate massive early galaxies. Spectroscopic confirmation programs have in most cases confirmed the photometric estimates rather than revising them downward as hoped. The tension between observations and lambda CDM predictions has grown stronger with each data release rather than weaker as statistical samples have grown. Theoretical responses have proliferated: modified dark matter models, early dark energy, primordial black hole seeds for early galaxy formation, modified gravity, but none has achieved consensus or reproduced the full range of JWST observations simultaneously. Webb has opened the crack in the foundation of modern cosmology that is growing wider every year, and the theoretical framework that will close it does not yet exist. I'll be sharing more similar videos in the future, so subscribe to stay tuned.